Next lecture to the wonderful beauty of quantum determining systems. Sorry for having just some sort of a jump in complexity compared to the things we did before. This is how the big things are going. It's always the case that we are now combining the things, network perspective, and also the geometric perspective, and this brings a more abstract view of system modeling, and consequently you see here base a little bit more abstract notation, but hopefully it helps you to understand the how models are combined together, and that's also something which is of interest. For the modeling paradigm, it's more on the theoretical side, but I start to talk about the practical side also. It's also interesting to use it for control systems design, and we'll talk about this not today, but on the next lecture. Where we also bring one example for using the perspective intelligence systems might be a good starting point for our control systems design considerations we might have. And just as a recap of last time, remember our direct portfolio. We in the middle we find this energy routing thing, which takes and combines all resistive elements, storage elements, and also sources that we call external variables. And I took the notation of the various vectors in the field. So here sources are made with the set of P, resistive R, so it's the calligraphic R, it's for storages, so not to be confused with our notation beforehand in the chapter 2. And there's energy routing in between, and this energy routing is now characterized by, well, practically by zero junction, one junction switch form generators. So these are the routing elements for power. Routing is power preserving structure, and then we revisited somehow telling us theory that in a network the instantaneous power sums up to zero over all network branches. That's the interesting fact, and we used it to define formally a so-called diode structure, which I want to go to this slide here, has some formal properties. Suppose we have a diode structure, it has the property that first we have this connecting property, that we have elements which combine with the flows sum to zero, and the apples combined FO variables summed up give zero. Here you find a combination of the Kirchhoff's voltage and current laws, just as a sum. That's the first thing. Second, E and F have the sort of property that they also have a similar rank, so we do not have more variables in F-folds and there, so they are some sort of conjugated, which you find here in this rank condition, and E and F and F and E also sum up to zero in some sort. Without that, it's nothing else. It's the theory of Kirchhoff's power and Walsh law. And at the very end, here the power balance, which is a theory in a most organic form. And then we say, okay, the diode structure is just diluting. We can have a different perspective on this and say, okay, take all variables F and T out of the vector space Rn, cross Rn, and then this equation forces F and T to live in a subspace. And therefore we have a geometric perspective, which you all learned in high mathematics and in the first semester of the vegetable grade. It's just a set-based version of looking at subspace of the entire space Rn. And we also know the dimension of the subspace is not R2n or R3n or 1.5n or something. No, it's n. And that's perhaps the thing we should know. It's just a geometrical perspective of grouping all together in the same formalism. And we didn't do that before. Now we do it before, and we didn't. And here it's combined. Okay. Our very nice example. I can come back to this in a second because we want to look at this in a certain amount of time to represent such structure. This is given right now because if you look at this equation, it's somehow implicit. You have E, F, E combined here. So you have an implicit notation of F and E summed up to 0. And as you all know, sometimes if you remember your Kirchhoff's current and voltage laws from linear electric network theory, you start to put one variable on one side. You say I1 is equal to I2 is equal to. And for some of the variables, you have on the left hand side of the equation, all the rest on the right hand side. And this is the same idea we want to do formalizing that. When did you do that? Well, it's quite a while ago. So in vegetable grade, for solving the network equations with Kirchhoff's laws. But now we want to formalize it a little bit. Why did you do it to solve them? And due to the fact that we, at the very end, we want to understand the dynamics of such systems, it's perhaps also interesting to have a more explicit notation where you have some of the variables on the left-hand side, which depend on all other variables on the right-hand side. So, given equation. So, therefore, let's try to do that. Suppose we start with the Dirac structure in the simplistic notation. It's called kernel representation, yeah? And with a rank of f equal to m, which might be smaller or equal than n. Okay. And now we select n independent columns of f and group them all together in matrix F1. This is not always directly possible to take the first 5 and then the next 10 are dependent. Sometimes you have to regroup them. You know that you have a permutation of the variables, which might take place if it's not given in that form before. I give you an example in a second. So you do this and group them in matrix F1, and all the rest is produced in F2. At the very end, you can write down F in a similar form with F1 and F2 as matrices where first contain the independent ones and F2 the dependent ones. And we do it similarly with E1 and E2. Consequently, you have to be careful. We have to do the very same with all of the variables F and E altogether, because the equation which there, take this example, which we have to respect this has a certain ordering for the matrix F and E. So first thing is to permutate everything, and then you reorder the equations. That's obviously possible. Okay, so if we do the same for E, we have also grouped all independent ones in E1 and the rest in E2. Then we can build a new matrix, which is F1 and E2. Sorry, E2, the independent ones, be careful. And we can combine them F1 and E2. And consequently, due to the fact that it's always independent parts, this matrix must be invertible. That's clear, because we took out only the independent ones. And then if this is invertible, well, let's invert it. We can write down the direct structure in the following form. We can always find a matrix. If it's invertible, the inversion is given here. Such it obeys the structure y is equal to z of x times u, with new variables u and y. So in the following form, that z is given by the inversion of this new generated matrix times this one. And the interesting fact is, with that, we have the variables, and u is comprised, is including vectors u1, f2 after regrouping permutation of the rest. So then we call it input and output vectors. So we have a combination. We just have an input-output notation by just saying, okay, take some of the variables which are independent and the other variables which are independent, and try to have just a image notation to project some of the inputs to the outputs that they are there, and this gives also this nice geometric view on direct structure. It's just another representation, nothing new up to now. It's just another representation, perhaps a little bit strange, but at the very end it makes sense to do so. And there is an interesting property about this matrix. You can check it at home. Even if it's not so complicated. You will find out that z is equal to minus z transpose, which is called skew symmetric. This matrix, and this helps with various calculations later on. If you want to find out some theoretical properties about the direct structure itself, this helps us for that. So it's perhaps interesting to know. Of course, the input and output vectors given here fulfill an additional equation, which is also not surprising. It fulfills the power balance equation of the direct structure. So if we multiply u transpose times y, we get E1 F1 plus F2 E2. It's obviously 0. This is due to the fact that we have a direct structure which is power conserving. It's nothing new, but important. We want to strive for a system perspective. So you know this from control engineering, you always have inputs and outputs, and here we relate inputs and outputs, and input times output is power preserving for the direct structure itself. Well, in the next step, we want to attach resistive elements, storage elements, and sources. Then this might not be true, but for the direct structure itself, it's power preserving. And in the explicit form, where z times u gives y, u times y is power preserving also. This is a fundamental fact. So this is something new which you might not know from your daily experience of input-output relations of the multivariable control things you learned in the lecture of Mr. Kluge. If you take any input and output variable, multiply them, you will not find this nice relation here. Typically, you take the outputs as measurement variables, and you have some inputs. It's not power preserving. Perhaps keep it in your mind. It's interesting to know. So up to now, well, we have a direct structure with this property, and with that, I want to come to my already spoiled example, and give you this input-output notation for the example beforehand. So go back a little bit. Here is our, here. This is the example which we deduced last time. We wrote down the Kirchhoff's current laws voltage laws and grouped all together in this matrix notation with the diode structure itself. We have the matrix F, the matrix E, and that's it. Okay, and with this, I want to start and do the regrouping. So take my notes, not to make too much mistakes, so be careful. We rearrange everything here right now. So let's start. Okay, so blank sheet of paper. I rewrite the matrix again to have it in our minds during our regrouping procedures. Then we have a 0 column here, then 0, 0, minus 1, 1, 0, 0, 1, 0, minus 1, 0, 0, 0, 0, 0, 0. Okay, that's the first one. Then we put here the negatives, FC1, negative of FC2, and negative FL, all the flows, FR and F0. And here I'm very happy. Same for the voltage relation. 1, 2, 3, 4, 5. Yes. 0, minus 1, minus 1, minus 1, 1. Again, a 0 column and another 0 column. And finally, minus 1, 0, 0, 0, 1. And here I'm put the vector of effort variables EC2, EL, ER, and E0, and all sums up to 0. Now let's do the permutation. Here it's quite trivial. Of course, we have the 0 rows, columns, sorry. Here is 1, there is 1. Here we'll find 1, there. And obviously, we can regroup the matrices differently. So this is called capital F. Here, capital E. And after my permutations, I end up with 1, 0, 1, 0, 1. So what I did, I put all the variables with zeros, all the columns with zeros at the very end, and that's it. And minus 1, 0, not to forget 0, 0, minus 1, 1, 0, and now the columns of zeros at the very end. And I permuted also the first and the second and the fourth row. No, the second and fourth row, so a third row. So that's it. Okay, be careful. In lowercase f, we do not find the same ordering of the variables f because we permuted all the variables. That's all. So this is not the vector here. So call it f tilde here, perhaps to make it more explicit. E tilde, something else. No? And plus all the zeros here all together. We need 1, 2, 3, 4, 1, 2, 3, 4, 5, and then we group minus 1, minus 1, 1, minus 1, 0, 0, and 1, and we get E here. It's again 0. And now you already see if I put two matrices together, want to highlight them with different colors. I'll take this matrix here. And the second one, orange. And over there, the first three. And a blue one, last two. Then we can define the following things. Oops, sorry. Take the pen here. We take this for F1, this one for F2. Here we define the purple thing as E1 and E2. And with this, we can write down F1, F2, E2 all together. We end up with the following. So if, yes?
You said that the order of the variables in vector F changes.
Yes.
Shouldn't it change when you convert columns, not rows? Just between the rows, it just change the order of the equation.
Yeah. We just changed the order of the equations, one thing. And therefore F is a little bit reordered. That's all.
Shouldn't that only be the order when we move the column?
Then you're right, yes.
We didn't change any columns.
No, that's true. That's true. But if you, yeah, you're right. I'm a little bit confused. Sorry. Yeah, you're right. That's true. So you can put it here. Yeah, that's true. Just change it in order the numbers of the equations. Okay, so put it all together. So F1 and Fe2 in one equation. So we get a new equation which includes, F1 and E2 in one equation, and we see that we get 0, 1, 0, 0, 0, 1, 0, 1, and then 0, 0, 0, 1, 0, 0, 0, and then 0, -1, 0, 0, just and -1, 1, and 0, 0, 0, 0, and 1. Okay, so what you already see, just by simple inspection. Sorry, that's something I wanted to draw. By simple inspection, you see here, it's not always the case, huh? It's an example here, but you see here an upper triangular form, which means I directly see it's invertible, because there is no 0 here on the on the diagonal, so consequently we find it's an invertible matrix. Consequently, we can say, okay, we're happy, and the results. So I don't want to do the calculations right now. It's something for MATLAB. Just a second. We can invert its matrix by simple the inversion. Okay, sorry.
I think there is a mistake with the HC. That one was not marked at this in the previous slide.
Okay, then there might be something wrong. Let's see. Perhaps I mixed something up.
F1 only had like 2 columns.
No. Then, oh, sorry, I was a little bit too fast here. Sorry, mistake from my side. Oops. Sorry. We need to goes over there. And the orange one, just the last part. Okay. Now it should fit into the formula. Okay, sorry for that. Okay, so obviously it's invertible, simple thing. We can invert it. Unfortunately, I have to say for such network equations, it's always such strange. Yeah, you get huge matrices to be inverted. Bad news, good news, it's typically very simple because we have very often just ones and zeros and a couple of and such a structure. It ends up very often in such simple structures. So therefore, you won't have so much problems in inverting it. For our exam, I will give you always simple things. I don't want to test you whether you can invert a matrix. It's not my question. I want to see whether you understood the thing. Okay, so putting all together. Oops, should be in red. We get Z as being, so after some calculations I did at home, we get one, zero, zero, and we get here minus one, 1, 0, 1, 0, and 0, 0, 0, 0. So with the variable u as being EC1, EC2, oops, EL, so the efforts and flows have 0. And for Y, we get minus FC1, minus FC2, minus FL, ER, and E0. And well, and here it mixes up. So that's clear due to the inversion of the things. And obviously, if you take U transpose times Y, you see it's always a multiplication of EF things. So you do not group all the F words and the flow variables separately. Here you have a mixture of it. And this is typical for this input-output representation.
One general question, last slide, how do we decide on the side of the plot? I didn't quite get that. For F1 and E1, for example.
Yeah. It's the main thing is just you want to find F1 being just this part here. Well, I was perhaps a little bit too far with my green box. The upper part is the interesting part. You see it?
Yeah, that I got, because when we need to go to the problem,
Exactly.
there's just 0 problem.
Yeah, that's it.
But so we just take the same dimension of the independent equation
Yes.
and like,
Yeah, that's it. Exactly.
and
Same for E2.
but if you have 2 independent equations, so then we have 2.
Yeah. Here we have 3 independent equations, and we get this F1 thing, and for E2 2 independent equations. Therefore, the lower part here.
But then we have to like inverse.
Yeah. We did it. Inverse form. well, the definition, well, it's a little bit arbitrary in that sense. No? It's not clearly defined. The main thing is, and I just wanted to show you that's always possible to do that. How you do it is your task. Basically, I want to say, okay, we always find in all current law equations and Walters law equations, a set of independent equations which finally gives set of variables is equal to a matrix times a set of variables of everything. That's what I wanted to cite. So we have this in the topic.
So the direct structure kind of predicts the input and output. We have no
Exactly. So we have, it predicts in just as it's an algebraic relation up to now. We'll come to the dynamics in a second. Just predicts and say, okay, given some of the effort and flow variables, all the other effort and flow variables. And it's just an algebraic mapping, that's all. And this is not very surprising because it's just the thing you did probably here in this lecture hall in linear electric networks by solving the Kirchhoff's current and voltage law equations without the constitutive laws of the resistors and inductors, etc. So it's a very same, but just collect all group together in a more algebraic setting. That's all. Nothing very special about it. So when you read the books the first time, you think, whoa, it's very, very unexpected. If you remind yourself on the things you learned in linear electric networks, electrical engineering, and you will find similar things that you, well, I think Olaf doesn't at your time never put all together and say, hey, the general structure is always this thing, and we would have ended at that point. Okay, so basically, we can say we have two representations of the Dirac structure. That's perhaps the main message I want to give. One is the implicit kernel representation given here. So we have all variables for flows and efforts grouped together in the vectors F and E, and a matrix F and the matrix E, which finally sums up to 0. This is a typical implicit relation you usually get if you formulate your Kirchhoff's voltage and current laws. Then you directly end in the implicit kernel representation. But as always in the linear electric network theory, you learned, okay, I can always put some of the variables aside, and it was a little bit tricky to define which one. During my studies, I had always the question, which one is the best one I should put on the left-hand side of the equation to get the result as fast as possible, as quickly as possible. And it's a little bit of practice. And here we get the theoretical result. It's always possible to do that first thing. And then you can represent everything in this input-output representation with Y comprising some of the variables of F and E and equally E, U. Okay, so up to now, we have just the static relation of the routing thing. Remember this diagram here from the very beginning, last lecture. We have just this routing structure. We have not included resistor ports, external elements, and storage elements. So now it's time to include everything and group all together. So they act on the Dirac structure. So what do? They define some of the variables ES, FS, ER, FR, EP, FP. Up to now, we group all these variables together and said, okay, we have we put ES, ER, EP in one single vector, same for F and for all the F variables. We stapled all together. And now it's time to include this information into our knowledge. And now we can also say, where does the because we are also super experts in modeling of the last lectures in chapter 3 and 2, where we learned that the state space system stems from the fact that we have storage elements in our system. So we just have to, where does the dynamics come from? Hey, it's the storage. We have just to consider the storage elements. And therefore, we should carefully look at the storage elements at that point. So going to this, and therefore, I want to define Hall Hamiltonian systems. Up to now, we just learned something about the geometric properties of direct structures. So it's more or less, say, Kirchhoff's voltage and current laws revisited in more abstract sense. That's all. Let's have a look at Hall Hamiltonian systems right now. And as already said, F is very well given by means of Fs, Fr, Fp as said. So we define F as being these variables and E as being these variables out of the vector space Rn and over for E. Now, we want to include the storage elements, and you might remember that there's always a relation between the flows and the stored energy and the efforts and the stored energy, and we want to use this right now. So let's have a look at this equation. You might remember our consideration of the our considerations of the storage elements. We said, hey, it's possible to deduce the complementary variable by means of the stored energy. And let's take first those storages where E is calculated by means of the energy stored derived with respect to one accumulated variable. Well, this is perhaps the thing you should remember from our lecture in chapter 2, where we introduced that we said, okay, we can define accumulated variables. That's the integral of efforts and flows. That's the first knowledge you should have. Second, if we then derive the stored energy with respect to one of these accumulated variables, I get the other one. I get not the other one, I get the effort or flow variable. Depends a little bit on the store I use. In the first step, we just look at the one, this storage variable, storage elements which produce efforts by means of the derivation. So capacitive source here. C5 source. Second, we also know that the accumulated variables define the state. Nothing new for us. So therefore, let's take the accumulated and therefore use the notation X directly. We can perhaps note this here. We have the accumulated variables here. Okay, so with this, we already define ES. Second, we know that Fs, the flow, is always the derivative of one of the state space variables. That's also something we learned. Due to the fact that everything points into the direct structure, we need a negative sign here. That's all. So negative sign comes from the fact that everything points into the direct structure. So it's due to our sign convention of, I put here the star
Okay, that's why. Okay. So obviously we defined Fs and Es for storage elements already. Second, we know that resistive relations have a constitutive relation given by means of a nonlinear function, perhaps, which relates flows in F-forward variables. So remember ohmic law, I times R gives U. Well, there it's not nonlinear, it's linear, simple, but it can always, you can always write it down as R times U, R times I minus U is equal to 0, so it's equal to that. You might have more realistic things, scenarios where it's nonlinear. So. Okay, so again, there's something which is relates FR and ER, and now we can say the following. A so-called fault Hamiltonian system is defined as follows. We take a direct subsurf route because it's our energy routing thing. Second, we have energy storing ports, which is given by means of minus x box and the derivative of the storage, the energy. FR and ER are not arbitrary. They have to belong to the space of resistive relation. So basically, this relation which fulfills that, this equation is fulfilled. That's all. That's how it was introduced for resistive relations. And then we have external force option. That's it. This is a dynamic system, isn't it? It's a little bit strange for us, but what do we see? We have states and its derivatives. The derivatives appear here as variables, and we have also states, but part of being part of a storage function. So basically, our energy function H. So it might be T or U. Application of the last chapter. I just want to be here because we mix up T and U in a second, and therefore it's already H as general variable. I should know this, that you're clear with that. See chapter 2. Okay, so we have dynamics in that sense, because we see a differential, some sort of differential equation. Is it the differential equation? No. What does it say? It says, well, it's not everything allowed. It's just allowed those variables to be which stay in the direct sector, so which are fulfilling the properties of the last subchapter. It's like filtering out some sort of the variables. That's all. Right? It's the subspace. So the dynamic system can be understood as we living on a subspace and this subspace is defined only by the energy routing elements. And that's it. That's the definition, or that's the understanding behind it. And I find it very interesting because it's like saying, hey, your ball has light everywhere, but now I fix it with a rope to the environment, and then it's dependent. And here we do, is it similar to that? Yes, because
we fix it, but it's different to what we've seen in chapter 3, because the other guy said, well, the panel goes along a circle. And we have constrained the free moving point mass anywhere towards to the circle. Here, I constrain the flows and the folds variables. That's a very difference. But it's somehow similar to what we've seen before, and therefore we decide, okay, it's a geometric perspective of the post-Hamiltonian system give. The direct structure constraint flows to certain subspace of the space that flows and folds, and F-forwards also. And one can say a direct structure or a system dynamics is defined by just selecting the allowed states. It's like you can do everything, and the dynamic system is nothing else than saying, well, I constrain the movement towards the one which is allowed. And then the question is, which component is the one which says what is allowed? It's the direct structure, so 0 junctions, 1 junctions, and all derivative. That's it. All others, and not to forget, the resistive part, because this constrains also some sort of the elements here also. So we have constrained by D and R. And this is only something, or this is something we already know, also from linear analytic network, I would say, because you might remember, you have these elements for the inductors, the capacitors, etc. And with both, you define the dynamics. Then you have the resistive elements and Kirchhoff voltage and current laws. And these are somehow reducing the space or reducing the number of variables. And here we put it in a more formal way and say, okay, dynamics is completely governed by means of the storage. And what are the constraints? Are the resistive force as well as the direct structure, so the routing force. So it's somehow comparable to what we've learned with holonomic constraints, but now on the integral part, so efforts and flows. It's not equal, it's comparable. Second, it's somehow implicit, so systems appear. So if we start modeling, we will never end with a state-space system directly. We will always end at an implicit notation. This is also one message, one can take away. Compared to our differential algebraic equations thing we learned in chapter 2 and also chapter 3. This is somehow a concept we know from multivariable control things. So if you're doing modeling, in practice, you will always end up with this implicit notation. This is not surprising, this is the standard case. So if they always depend this path to go for an explicit notation. And here I showed you first, it's always possible. So if you struggle with going for the explicit notation, then you can bear in your mind and say, okay, I have to work harder because I should find it because it's always a good thing. First thing. And second, is it step to do if you want to go for a safe system, if you want to use the multivariate control things of the lecture or multivariate control, for example. Okay. Now I want to go back to one assumption I made in this slide. I said, okay, let's look at this slide of F-fold definition. I said it is always possible to define an F-fold variable by means of the energy storing elements, and you might remember this is not true. This is not true because in chapter 2 we learned something like, this is true for some sort of storage elements, basically C-type storages, where if we derive the stored energy with respect to one variable, basically outside storage elements, with one of the state variables, I get the F-fold variable. But this is not true for the other side of storage. There I get the flow variable based on the storage function. Then there's some sort of, but then there's the need for defining organized quater-Hamiltonian system for different types of storages. Is it possible, or do we need two, or how does it work? And the answer is, well, it's quite simple, because you can do the following thing. I want to put here as blank slide here in between. Here. Suppose you have a C with EF variables here. What can you do about it when you want to mix up E and F? How can you transform a C into an L type storage? Nice question. What element has to be put in between to mix the variables? We learned something about that in chapter 2. Yeah, a gyrator. So if you have a C and put a gyrator here in between with beta equal to 1, you have a mixture of the variables, you get Fe. And so if you put a box around it from here, the C looks like an L, isn't it? And this is something we can use. So you can transform any C into an L and an L into a C by just putting and it behaves similar. Suppose you have a network with capacitors, you can look at the same network with a gyrator and inductor, and vice versa. If you have a network with inductors or inductances in between, you can put a gyrator in between it and transform it into a network with just capacitors. So consequently, it's not a big deal to put everything in the L-type storage function. We just place always gyrator in between. So it's the same perspective. So consequently, we do that here because it was very helpful to have a storage type function given here. Why it's so helpful? Well, we get always the same notation. We have always E is derived by means of a storage function. It helps to keep the symmetry. It helps to have all the equations similar or same. And this is possible. Is it surprising that's possible? No, because we know from our considerations, for example, for the mechanical domain, that we can mix up the variables. It's not very well defined whether we use for E the velocity or for E, the fault variable, the impulse, derived, important. So it's arbitrary. So what I want to say, it's not surprising, and mathematically it's easy because we can put a generator in between. Therefore, in literature one speaks of the so-called thermodynamic framework because this framework, it's always the case that the variables used where we define to generalize space over fluid. That's the point. So we have always the fluid and the state variable. That's the only thing for helping us to keep the things as simple as possible and as similar as possible. That's the point. And or put it in the table. You can define it in an electric way to define the flow of the current, and in the magnetic field, the flow over the voltage. And in or for the mechanical part, if we look at potential energy or potential translation, if you like, elastic translation, then we define velocity as our flow variable. And if we look at kinetic objects, then we use the force our flow relation. And with this in our mind, we can either mix up the variables by ourselves, or we put a generator in between. It's like putting an L type, C type, story type thing I discussed now. And why it's called thermodynamic framework? Because in thermodynamics, we have just one type of storage, which is the entropy flare. And there we look at exactly one. Okay, so with this in mind, I want to give one example first. So suppose you have this oscillating mass, which is attached via a spring to the line, which is given here. Now we want to do the modeling and look what happens. Well, the Hamiltonian, or say storage function for a spring, you know, let's say half k spring constant xs squared. So xs is the displacement of the string. It's potential energy with energy state xs displacement. Now let's do the definition as before. Xs dot gives the flow variable, the negative flow, so Fs force. And second, if I do the derivative of the energy function with respect to the Xs, I get Kxs for the F variable. Nothing surprising, we did this before. Now, this is not the only element which is present here in our simple example. We have also the mass, but the mass defines kinetic energy. I assume the friction in this example first place. The Hamiltonian, so kinetic energy, basically the storage function or kinetic energy function or Hamiltonian, is given by a half 1 over m xm squared. Now we have to be careful because we define the energy state as being momentum. Because with this, we can define xm dot is given minus m here using Newton's law. The force acting on the mass defines the momentum derived. That's pure Newton. Or we can also say we derive the energy function given here with respect to the state variable and get exactly the F variable, which in our case for the kinetic energy is the velocity. Now we group everything together. That's the first step, just defining the elements. What is the routing element? It's the diag structure. The diag structure says, okay, we have flows who sum up to 0.
which in our case is given here, and F forwards, which sum up to 0, which is given here, obviously is power preserving. And if I do so, and write down the Dirac structure in matrix form, I end up with exactly this one. Due to the fact that this is a very simple example, it's not implicit, it's definitely explicit, it's very, very rare instance that we end up with an exclusive notation. It's due to the fact that, yeah, it's so simple. But we can learn something out of it already. What do you see from the first equation? If you look at it, what do you see here? Something you learn in other lectures. In general, what is it? No idea. Looks like, but it isn't exactly, I would say. I think you should know. What is x dot is equal to ax plus bu? Like this already? Looks like a state. Looks like a state-based system. But there is something mysterious about it, isn't it? What is different to a state-based? So x dot is given here, you see it here, okay? There is something which we can consider as an input because it's an external force. Okay. Mm-hmm. So u is existing. Huh?
You don't use x,
Yeah,
but rather use the derivation of h.
exactly.
That's what.
So what we can learn is what we directly see that the states of a system are defined via energy functions, which is given here, namely h, which is the sum of the energy of the string and the mass. So it gives additional structure to what you know from state-based systems. We know on the left-hand side we see the dynamics and the all the derivatives of the states. And as states, we know that it's the derivative, the partial derivative of the energy function of the entire system with respect to the states. So if you think of this equilibrium states in multivariate control, you can say, okay, your states are really the storage function derived with respect to the states. That's it. And the matrix A, where does it come from? If we look here. Something you might have wondered about perhaps beforehand. Where does it come from? In this simple example, it's not always true. This 0, 1, minus 1, 0 thing. Something we discussed before. No? It is used to measure, yeah, this is one property, but there is something where it stems from. Does it come from string and mass relation? Or the Newton's relations, the Dirac structure? I would say exactly. So, what does he take away? The matrix A, we know somehow, it's not all, but always the case, but somehow includes the Dirac structure, includes the routing. This is not so surprising. Just a second, just to make the point. But that's something, this is something you might have wondered about. Well, I did it during my studies, that somehow this matrix A represents the interconnection of the various elements. And here you see, yes, it does, because it's part of the Dirac structure. We want to formalize it in a second. It's not always the case.
Not your question, sorry.
The end predetermined property lies in this system.
Exactly. Exactly. It's, but we will elaborate on this, to pick up your points also. So part of the matrix A comes from the Dirac structure, and we know the Dirac structure is powerful, first thing, what it said. Here we see it's two symmetrics, so consequently mathematically it's two symmetrics. City plays a major role in terms of the culture zone, and now we learn a matrix A comes from the routing thing. Is it all? That's the question. It's only routing. Unfortunately, the answer is no. It's more than that, and you might have an idea which brings problems into this simple things. I give you a example which shows that's not always true what I said up to now. Now suppose you have just a simple DC machine which with its equivalent circuit RL and a shaft which is a inertia produces a torque and angular velocity. We have external voltage applied to it, and we want to model. Okay, in a fault Hamiltonian system framework, that's all. To understand things a little bit. Okay, so first of all, let's look at the storage elements. We take the inductor with Hamiltonian 1/2R XL squared with the magnetic energy with XL being psi, the magnetic flux. So in the stage, we modeled here the system with the flux relation. To keep the thermodynamic framework, or say we put the L into a C. Consequently, we get H derived with respect to XL and gives the flux variables, consequently the F of there. We have a rotating mass of the second storage element, so which is kinetic energy. There is the same story applied as before. And for the moving mass, just in the rotating framework, we end up with this equation. So the total energy is the sum of the energy of the magnetic part and the kinetic part. We sum it up, and that's it. In addition to that, that's important, we have resistive elements here, so basically dissipation. We can say, okay, there's UR is equal to minus RIR. The negative sign comes from the sign convention again. It's our sign convention. And we have friction or damping elements. In our case, I assume simple linear friction. So proportional to the rotational speed, I get a momentum. Again, sign convention due to our convention of the direction. And finally, we have routing elements. What is routing? Routing is the connection, so the period voltage and current laws, and Newton's law, and a transformer, which we know because we have a transformer like the DC machine itself, so the transformer and effective. So therefore, grouping all together, we have the current equation, the voltage equation, the flow equation, if you like, and therefore we have the direct structure. And if we, sorry, too fast. If we put other things together, we end up with this equation here. You can do it at home. Again, here I wrote down the variables, the state variables directly, but you might directly see if I do the derivative of this equation, H with respect to XL, I get the first state, and H with respect to XJ, I get the second state. So this is somehow different, but you get additional structure here.
So first of all, you see again an input variable. You see the states over here. You see the derivatives of the states, and here you see the matrix A. What is different to what we've seen before?
Well, the property value of the on the which are
Exactly.
we have to make it items.
Yeah. It's obviously more than just the diet structure. Because we see here the resistive elements also, which are entering this story. And that's what I said when you start learning something about linear electric networks. You're learning something about how to solve these equations. And then you have two parts, the Kirchhoff voltage and current laws, which you have to solve for, and finally the resistive elements, which have this relation which enter in your equations, which you use. And those together finally define the matrix A of the state space system. So that's the first message. So the diag structure plays a role, and the resistive elements play a role for this patient. The interesting fact is, when you do the calculations, you end up with these two matrices, which are given here. And this is interesting enough, very, 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 very often possible to separate the matrices into two parts. One, which is given here, which is skew symmetric, as you said, like in the example before, which is completely defined by means of the diag structure, routing, and a second matrix, which groups together all the elements which belong to the resistant part. So, and it's always in this case, it's always defined in that way. So matrix, diag structure part, and the dissipation part. This brings additional structure to the matrix A. And that's why you see it directly, I think. That's why it's so interesting. Because if you know what is responsible for routing, has a different impact on things like stability, like dissipation. It's clear. If you have direct influence and see it, what is dissipation in your system, and you might act on that. Or you see some sort of stability property might be in your hands by just looking at the structure. Therefore, it's interesting for us. We will discuss it next time. Just as a takeaway, and then we want to do the questionnaires, not to forget for today, and we should have enough time to fill it out. I want to make the point that this result, which we learned here from the DC machine, can be deduced in general. Go here over the proofs. If the resistive structure is linear, which is very, very, very often the case, then we can write this composition of the diag structure as a linear mapping. Then you can find such a so-called input, state, output, fault, Hamiltonian system with feed-through. And there you get the matrix J, which is skew symmetric. The matrix R, which includes all dissipation elements. We have here the states, similar matrices for U, and you define the Y, the output element, as given. So get additional structure for your state space system, where you find here the matrix A, here the matrix, oops, all together, the matrix B, here the matrix C, and at the very end, here the matrix D. And they all obey a certain structure as given, which can be deduced. And that's just wonderful because it helps us to, if we have more structural information about the system, you might imagine it must be easier to deduce control system strategies. About this, we want to talk. But today, I want to stop here with our topics because I want to do the questionnaire right now. If not, there. Would be nice if you could fill it out.